You can pick up your quiz if you have not done so. Okay, so I posted the next homework sets. So instead of the way that we did it previously, so this time I'm only give you the actual homework in the book instead. I hope it will make it a little bit easier to follow. So, so the way that you'll do is you'll finish all the homework and you can scan them and you can upload it on there. And I mean, uploading is only to get you a grade. So we don't grade them. So we'll post the solutions at some point. So that's how it's going to work. Any questions on that? Hmm? Yeah, I think for the moving forward, I would put it this way instead, because the previous one I found it was a little bit, some of the problem was a little too difficult. I was expecting too much. So make it a little more, hopefully will be more doable moving forward. And also, what I'm going to do is over the next couple of days, I'm going to make a list because the book has too much contents. There's no way that we can teach everything from the book. It's just impossible. I mean, ideally, I would work on one section, one lecture, sometimes one section, two lectures, we cover everything. There's too many equations to derive. So what I'll do is I'll make a list. I'll tell you which section is kind of you have to manage, you have to acquire. And some sections only, maybe the subsections are actually required for you to get really familiar with. And the additional contents, like what you guys, if you're advanced, you can study them and get familiar with the rest. But what I'm going to give you is the barely minimum, which means if you read this section, you do the homework on this part, you should be good for the quiz, and you should be good for the final exam as well. But that's kind of the barely minimum coming out of this class is that I got something out of it. What really I wanted is everybody come out of this class saying, okay, I did get something, right? But not everything, but something. Because I mean, if you look at that book that was sick, right? So it's really, I mean, it's a lot of to study. It's not easy. I know it's especially when a lot of us are not so much doing math anymore. So when you get to math equations, it is confusing, and I understand it. So that's why I'm going to make a little bit change in the process of teaching. But you guys let me know, what you think and what you feel good, what you feel bad. Come to my office hours. I know that there are a couple of students coming to my office all the time, but you guys come, in groups or individual person, either way, welcome to talk to me. Give me feedback and tell me what you like, what you don't like. Tell me what you understand, what you don't understand, so that we can continuously make improvements. I mean, that's how we can all, work together to make this class worthwhile for your time and for my time too. So for today, I'm going to try to cover a little bit of section 9.3, common mode rejection. And we're going to only cover the first, we're going to cover only 9.3.1, the MOSFETs. The BJT is very similar. The only difference that there's R pi in the process. Make it a little bit more complex. I mean, that's it. You're not really seeing too much of a difference. And then I'm going to go over, if I have time, we're going to cover a little bit of 9.4. And 9.4, we're going to cover only 9.4.1. Again, also MOSFETs. not when we don't have time to go to BJTs. So that will be today. And we're going to skip 9.5, which is a differential amplifier with the current mirror law. I know in the later chapters, sometimes we have to refer back to here, but assume that it's given. So if we use the equation from here, it was given. And then next lecture, we're going to focus on the last section for 9.6, which is multi-stage. I think by the time we get to 9.6, it will be really interesting because you can see how things are looking so complicated, but in fact, they're very simple. So by that time, you say, okay, well, I thought it's going to be miserable, because they're not a single amplifier, but there's two, there's a differential amplifier, but not only just differential amplifier, but there are two of them. But then there's also multi-stage. But you'll figure out, well, if I know how to do one by one, it's actually fairly simple. It's not that difficult to master the contents. The other thing that I hate to mention it here, but this book has gone through the 8th edition. But I found the 4th edition of this book was the best edition because it covers like stuff from simple and then more difficult and more difficult. But these new editions, they start right from the most difficult part, and then they go to the easy part. So that makes teaching difficult because, but anyway, so I think, so I'm gonna make a list of each chapter, what you need to really to read and to do the exercises and examples in the book, so that you don't have to read the whole chapter. I know reading the whole chapter, this much of chapter take a lot of time to do it. So that's what I have to start today. Any questions? Okay. And then also, of course, we're going to have a quiz on Wednesday. And the quiz of Wednesday is going to cover only section 1 and then section 9.1 and 9.2. So again, if you have done your homework, if you have done, like I sent an announcement yesterday, I'm telling you that, if you do these problems and these examples, so if you know how to do those problems, examples, you will make 100% of the quiz. So I'm very honest, okay? And I'm trying to help each of you how to pass the class and how to get a good grade. But if you're not doing your homework, if you're not reading the text and not doing the stuff that I announced, it will be difficult for sure. And if you have a problem doing the homework or any homework, come to see me. Don't get stuck, like hours cannot get a solution one problem. That's not very good because you're really wasting a lot of time. But of course, you need always to get a first try before you come to see me. Because if you don't try, you come to see me, I tell you how to do it. And when you turn around, you'll forget. So that's important that you try it. And then I'll explain it. And then you'll really figure out how to do these problems. Okay, so today we're going to look at the common mode injection. In this common mode injection, what you see is to start with is a differential pair of MOSFET. And for BJT, of course, it's the same thing. Simply replace the MOSFET with a BJT. The only difference I want to mention is that here, initially, in the original discussion last week or a week ago, we had this current source only. Now we know that current source comes with output resistance. That output resistance is typically the RO of this MOSFET. So, to represent the RO, we put a RSS in parallel with it. So this is the DC circuit. Now think about this DC circuit. What happens when we get the small signal equivalent circuit? So apparently, this becomes an open circuit, right? Because it's DC current. And this VSS is a voltage source, so this becomes the ground. And on top, you have VDD, which becomes the ground. So you can see that both RDs are going to be connected to ground, and this is connected to ground, and RSS is going to be connected through source to ground, and this is open circuit. So in a common mode in rejection, what we are looking at is what happens if we have a VCM, which is a DC signal. The capital means DC. And then we have VICM. I means input, lowercase cm means AC. So you might say, oh, what does it mean? Well, what it really means is here. If I draw a small diagram over here. Oh, you guys know what happened to my pen doesn't write last time. Yeah. Oh yeah, the Bluetooth, right? So, okay, let's see how we get there. You guys are genius. I mean, huh? Oh no, it's not loose. It was writing the other day. Bluetooth, okay. Apple Pencil, not connected. You're right. So how? Well, let's forget. Huh? Should we forget this device? Apple Pencil, and then we'll add it. Should we? Do we need to do something on here? Do we double click or something? Okay. If it doesn't write, can I borrow somebody else's pen? Ah. Let's. Yeah. Add a pencil. Oh, it's connected now. Okay. Good. Hopefully it'll work. Okay, it works. We solved the mystery. Okay. So what I'm gonna do is like if you have an input, we can have a different input. Like in this case, if you have this, and this is, if you look at this one, if this is the X, so we call this like a small signal because it's small. Okay, so big and small really they do mean. So in the DC, for example, you have 1 volt, 5 volts. Those are DC. Those are large signal. The small signal means a few millivolts, like 5 millivolts, 1 milliamps. So they are typically in the difference of 100 to 1,000 or even more. So that's why it's called small. So if you have an AC signal that's very small, and on an oscilloscope you can see them. But sometimes if you have an input, well, you have this. This is your X. And then you have a signal like added onto a DC. So if that DC, let's say, is 1 volt, and you have this millivolts of maybe 5 millivolts. So that 5 millivolts added on top of 1 volt, they becomes a small signal, AC signal on top of DC. So what we are doing here is we have VCM plus VICM. They're both, so VCM is a DC, ICM is a AC small signal. So small signal added on top. But the difference between the VICM and VID we applied last week was VID is a differential input. It means we add half on this side, we add half on minus half on this side. So together you get VID. But for YCM, common mode means, remember, common mode means the same. They're common, they are the same. So what it means here is we're going to add VCM plus VICM on left side. We're going to add VCM plus VICM on the right hand as well. So apparently the two input are going to be exactly the same at the two gates. And we're going to take output at the drain of each of the MOSFET. So you might say, well, last week you demonstrated that with the common mode input, the output is 0. What are we talking here? Well, you're right. So that's the key. When the devices are matched, this output are going to be exactly the same. And the output between the VD on this side and VD on the other side, which is here we have VO1, VO2, is going to be 0. That's correct. But what we're going to talk about today is really what happens if these devices are not exactly matched. Okay, can you tell me what other things can go wrong in this circuit? Go wrong means they're not exactly identical. What other things you think can do that? A few things that we can look at. Yeah, go ahead. No. Here we have the input same on both gates, so gates grounded is not considered here. Yeah, but I mean just the circuit. Look at the circuit. What would be possibly make a difference so that these two circuits are not identical? Somebody said resistor. You have two RDs, right? R is a resistance. Resistance is a machine or handmade something. When you make two something, you want to make them identical, but in reality, they will never be identical. There will be always a small difference. So when you buy a resistor, you can buy resistor with a certain tolerance. That tolerance means you buy resistor at 1K, it doesn't come with exactly 1K. Most of them will come to 1K, but it will be 1K plus 2% or 1K minus 2%. That is a 2% resistor. You can also buy a 5% resistor, which means it comes 1K plus and minus 5%. And you can buy a 1% resistor or 0.1% resistor. The higher the precision you have, the more expensive. So RD can go wrong. There could be a small difference. If you buy 1% resistor, which means the two resistors can have a difference of 1%. That 1% will be sufficient to cause the output to be different at the two drain. And then there will be difference at the output, VO. Okay, that's number one. What else? Yes. You're right, the transistor. So the transistor width and length can hardly be exactly identical. It could be a little bit different, and plus other things too in the MOSFET. So the result of that change is the GM, basically, the GM. VA cannot be exactly the same either. So GM is going to be slightly different. And it could be 1% or 0.1%, whatever that percentage is going to be. So that can cause this thing to change. So which means over here, we identify two things that can potentially go wrong. And that thing go wrong will make this output different. So the output you're going to see is VO1, VO, eventually VO equal to VO2 minus VO1 is not 0. Okay. So in ideal situation, let me open my book so that I don't write anything wrong. You guys, DC offset. So what we are doing here is like when we do when we look at the circuit here, and we can do, of course, we can do the DC analysis, we can do AC analysis, but for DC analysis, we really don't care because I mean for DC signal, it's always like because it's a large signal, so we are not so much concerned about the symmetry or matching of the transistors or the resistors, because eventually the difference is very small. But what we are worried is the AC signal, because the AC signal, the input is very small. So every little difference makes a big difference at the output. So that's what we're concerned about. So over here, what we can do is first we can draw an equivalent circuit. So earlier, one student come to see me saying, what are we drawing? How do we draw? How do we know that the circuit is representing DC or AC? But if you look at the circuit, this is representing a DC circuit because you have voltage. You have voltage on both sides and you have DC. So when we draw the AC signal circuit, we'll have the DC current open, and then we have the DC voltage short. So in this case, we're going to draw the AC circuit. Oops, I forgot resistor here. All right. So this is the circuit that we draw for the AC. When we draw AC, you can see the top one is grounded because VDD is ground. The bottom one, VSS, is ground, but we do have RSS that is left in the circuit. So RSS is the output resistance of the current mirror of the current source, but that's not shorted, but the current is open circuited. So now we can look at the output over here. So we call this one VO2, and then, yeah, so VO1, VO2, and then, of course, VO is still VO1, VO2 minus VO1. But as we said before, if everything is considered like identical, the actual output will be 0. So we're going to first derive the expression of the gain, and then we're going to look at what happens when the parameters are not matched. So okay, so this is the equivalent circuit that we drew earlier. So now what we're going to do is we're going to draw the this currents in this circuit. So in MOSFET, the current flowing here in each one is I. When it's symmetrical, again, we're talking about symmetrical. Yeah, we're not talking about the M-match device yet. So each current is I, and there's 2I here, and then you have I on each side. So in this case, you can get VO1 equal to I times VO1 is minus I times RD, and VO2 is I times RD as well. And VO equal to VO2 minus VO1 equal to still 0, still 0. So this is for the actual, if you think about the current flowing in each device, you'll get that. But we can also draw the small signal equivalent circuit. Now in this case, we have RSS at the bottom. So the idea that we're going to, I don't know if you remember, when we did the differential input, we actually eliminated this one. The reason is the differential current flows from this current to this current. It doesn't flow this way. So that's why there's no current. So this becomes a virtual ground. But for this common mode, the current has to flow somewhere. So the current cannot flow anywhere if we don't have this RSS. So that's why it's important to have RSS. But having this RSS here will make our calculation more difficult if we use a pi model. That's something we explained earlier. So the best way is to use a T model or hybrid T model. So with the T model, we can draw the circuit like this. So we have RD, which is ground over here. We draw one side first. And then here we have current. And then we have current here. And then we have RSS on this side. And this is your RD. And this is your GM times VGS. And here is your ICM input. So we draw this circuit, but the other half is really identical. So we can draw the other one. this your R, this your RS. This RS is a equivalent resistance. Okay, and then we have output VO2 here, and we have VO1 here. So that's a identical circuit. So this is GM2, VGS2, this VGM1, GM1 times VGS1. Okay, so we have that. So what you're looking at is, let me see what is the expression is going to be for this. So, and then this RS equal to 1 over GM. This is something where we derived a long time ago. Okay, so if we want to get a VO1 in this equivalent circuit, we can use this current times this resistance plus the current over both sides times this resistance, we get this voltage. And for this voltage, we can get this voltage over here. So, and then we can use VO2 is basically the current times this resistance, right? So we hold here, so we can derive here. Let me see if we have, yeah. So I redraw the circuit on the next slide, and we can write, we can write the equation over here. So in the book, for simplicity, what they're doing is they separate this one into two circuits. The reason is, if you look at the voltage here, the voltage here is 2I times RSS. So it's 2I times ISS. But if I look at each individual circuit, if I comes in here, how much resistance would you need on over here? So the voltage here has to be 2I times RSS. Since this is I on one side, so this resistance here has to be 2 RSS. So this one is exactly equivalent of this one, but replacing this with 2 RSS. Because the voltage here, current here is the same, so the voltage here are the same. So basically you can connect these two. So in theory, you can connect, just to make sure that we understand what we're doing. We can connect these two in series, in parallel, because the voltage are the same, right? So the voltage here, I want to write here. So this Vs is equal to I times 2 times RSS. Or here, the voltage here is Vs equal to 2 RSS times I, which is the same. And same on this side. So 2 times RSS times I. So because these two voltages are the same, so we can put them in parallel. So when you put them two in parallel, how much resistance do you get for equivalent resistance? Divide by 2, so you get RSS. So it comes back to this. Right? So that's easy, okay? Okay, so now you say, what do I do now? Well, basically, what you can easily do is here. So instead of this, we can put this resistance as 2 RSS, and we can find out what is each voltage each is going to be. So let me do it on this circuit here. So let me do let's see, make it a little bit simpler. Just trying to, okay. So instead, we're going to make this one here 2 RSS. So I'm going to disconnect over here. So this one also 2 RSS. So by doing this, you can see that this is, I want to make sure that we understand what we're doing. Here is Vs, here's Vg. So first of all, can you tell me what Vg is going to be in this circuit? So Vg is given as oops, I didn't want to quit. So Vg is given as VICM. But Vs is given as I times 2 RSS. So how much VGS? Can you tell me? So Vs, the I current coming this way, so this is Vs. Okay, and this is VICM. So VGS is going to be VG minus Vs, which you can write in two ways. One way is to write as I times 1 over GM, or you can write as VICM minus VSS. No, VSS, minus VS. Minus VS. So we can write it this way. So VGS. So once we know VGS, you can see from here we can derive, let's say VO1. Let's do VO1 first. So VO1 is going to be minus RD times I. But I over here is like a really we don't know exactly what I is, so we cannot really get the relation between VO1 and VICM. So instead, we need to derive from this equation here and this equation here. From these two equations, we need to get the relation from I and VICM. Okay, so if we look at this equation here, so this becomes VGS is I times VGM. So it's going to be VICM minus, okay, so let me do it this way. I'm going to plug in this VS. I'm going to plug in VS over here. So I get VGS equal to VICM minus 2I times RSS. So then we have VGS, VGM. Okay. So we have we can get VICM equal to VGS minus 2I times RSS. And then we can plug in this one. So by VGS is equal to but VGS equal to where's VGS? VGS also could I over 1 GM. So minus, oh no, I'm sorry, I made a mistake. Okay, so let me start off over here. So VGS is this one here. So VICM equal to VS plus I over 1 over GM. And then VS, we plug in VS over here now. So we get I times 2 RSS plus I over GM. So this is what we get here. Okay. So now we have VO1. Let me erase this one. Oh, that's from the previous writing. I cannot erase it. Oh, it's okay. So we got VIS as a function of I, and we know VO1 is also a function of minus RD times I. So from here we can get our gain, like our gain. Our gain will be VO1 minus divided by ICM. So we got VO1 is minus RD over 2 RSS plus 1 over GM. So that's the gain of VO1. So from, I hope you guys follow me. Maybe I can explain one more time. Is we can write VS is here, 2 RSS times I, and VGS with ICM is equal to
this plus this, and VGS equal to I times 1 over GM, okay? And we ICM equal to this voltage plus this voltage, right? And then our VO1 equal to I times RD minus I. So we plug in that one, we got this, and then we know this one. So we take the ratio between VO1 and ICM. The I is going to cancel, so we got VO1, ICM, I is going to cancel. So the numerator is RD, the denominator is, numerator is RD, the denominator is 2 times RSS 1 over GM. So that's the gain that we get. So similarly, we can, what do they call this one? They call this, let me see. They call this VO1. Yeah, I guess we can just leave it for now. I guess you can also write, in this case, we can, let me see what else, let's like. You can write VO1 equal to RD over 2 RSS plus 1 over GM times VICM. And similarly, we can write VO2, there is a minus sign, sorry, there's a minus sign. And VO2 can be written as minus RD divided by 2 RSS plus 1 over GM times VICM. So in this case, so apparently if you take VO1 minus VO2, you will get a 0, right? So still, but you're saying, okay. So what happens next is going to be really interesting. What happened? Come on, mode input. This is not good. I'm sorry, I made some mistakes. Okay. So what we are doing here is we're going to look at what happens to the previous equation. Let me write this. I don't remember this either. So I'm going to write this VO1 equal to VICM minus VICM RD over 2 RSS plus 1 over GM. And we have VO2 equal to minus VICM times RD divided by 2 RSS plus 1 over here. What I'm going to do is I'm going to add, let me make sure this is right. Yeah, 1 over GM. Yeah, that's correct. So what I'm going to do is instead of talking about RD and GM, I'm going to add this symbol to use each transistor. Okay, so I'm going to call this GM1, this is GM2, this is RD2. And then you can see that one RD1 equal to RD2, GM1 equal to GM2, VO1, VO2 minus VO1 equal to VO equal to 0. But one RD1 or GM1 does not to GM2. This is where what happens. When RD1 and RD2 are not the same, or GM1 and GM2 are not the same, you're going to have a difference. So what they're doing is we're going to look at, we call this dirt RD. So assume RD1 equal to RD plus dirt RD. I don't know which one they use the plus, which one they use, yeah, okay. So they are using this, actually they're using minus. So I'm going to use the same symbol. Minus delta D and RD2 equal to RD plus delta RD. So look like there's a small difference between these two. So one is up, one is down. So the total is 2 times delta ID. So one RD goes like 1 milliohm up, the other one goes 1 milliohm down. So that's what we do it. So we can plug in these numbers in to get here. So if you get VO1, will be VICM times RD1 minus dirt RD divided by 2 RSS plus 1 over GM1. And VO2 equal to minus VICM times RD2, RD, sorry. This no longer has 1 here. But in this case, we're going to assume that GM1 is equal to GM2. So hopefully that helps to one over GM is RD minus this RD. Okay, sorry. So RD plus dirt RD over 2 RSS plus 1 over GM. So we do one by one. So the very first time, like we assume RD1 and RD2 has a small difference. And then next we're going to analyze if there's difference between GM. So in this case, we can use VO equal to VO2 minus VO1 equal to minus. So you can see this RD component will actually cancel. So what's left is really delta RD in the output. So, but this is going to be the same. This is going to be the same. So what we get is 2 times dirt RD over 2 RSS plus 1 over GM, and then times VICM. So in this case, we're going to get this so we're going to take the ratio. So this what we call this VO2, VO1, and yeah. So we're going to take the ratio between this two. We call this A, common mode gain, which is going to be VO over VICM. Actually, there's no minus sign anymore because VO2 is minus VO1. So actually, it's going to be, yeah, it's going to be actually minus sign, which is okay. Yeah. 2. Yeah. So, and then over here, when we take the ratio, we basically simply move this 2 times dirt RD over here, divided by 2 RSS plus 1 over GM, plus 1 over GM. And also, of course, there's a minus sign. But when we can take the absolute value, then the minus sign will be gone. So this is your common mode lake gain. And then from here, since typically RSS is much larger than 1 over GM. So you might ask how larger. Remember, RSS is the output resistance of the current source, which is typically in the kilo ohms, like 10, 20, 50 kilo ohms. But GM is usually in the single digits of milli, like 5 milliamps, 1 milliamp per volt, something like that. So if you take 1 over GM, so 1 over 5 millivolt per ampere, you get how many? 200 ohms. So 200 ohms compared with 220 kilo ohms, that's very small. So we can basically get rid of that 1 over GM. We will simply have A CM equal to minus dirt RD over 2 RSS, which equal to dirt RD over RSS. I think I'll get it right. Now, of course, when you guys go to the book, you might find actually a difference because I think in the book, they use delta RD is on one side, not on both sides, and also they use R1 is bigger, R2 is smaller, so that finally you get this as a positive. But really, it doesn't matter because what you're looking at is the absolute value of the output has a gain of this much. This is the common mode gain in this case. So, and then what in the book, what they're saying, okay, so if ACM equal to, let me take this absolute volume now to be dirt RD over 2 times RD, which now I'm going to follow the book because in the book, possibly what you can do is instead of adding one side minus dirt RD, the other side plus dirt RD, you can put only on one side. So the absolute difference, or in other words, you can also do something like this. You can also like divide by 2, right? So if you divide by 2, and actually maybe if I do this, so you guys have something to follow later on. So instead I'm gonna do this plus sign, this minus sign. So I have over 2, this over 2, and then this will be over 2, and this over 2, and this will be this no 2 here, and this will be 2RSS. So this will match what in the book. So now we have this, but we can rewrite this one. Oh, sorry, this RSS. Okay, let me see if I get it. Okay. So yeah, I got that right. So 2 times RSS. And then I can rewrite this into RD over 2 RSS times dirt RD over RD. So I simply manipulate this by multiply RD for the numerator and RD for the denominator. You might say, what are you doing here? Well, the idea is that if I do this, you can see the first term is in fact the gain we get for the differential mode, for whatever. That's the actual gain of the circuit. The second term is related to the change of RD. If the RD is matched, apparently the common mode gain is 0, right? Because dirt RD is 0. If you have RD big, and your change will be big. So in this case, we have this, they define the difference is, they call it common mode rejection ratio. Common mode rejection ratio equal to the differential gain over the CM gain, this. And the CM gain, the differential gain, and so it becomes okay. So what was the differential gain? Do we remember the differential gain? One over GM. Very good. It is I think it is GM times RSS. Hold on. GM. Well, I mean, basically, if we know that we can possibly go back and derive it, because that gain is going to be GM times VGS times RD. So, and if we know, I mean, sorry, V out. So VO1 equal to this, right? So, and then so A equal to differential mode is VO1 over GM, and no, not with GM, with VGS is going to be minus GM and RD. So this is what you get for the gain, for the differential gain. So now we're going to plug this AD to the common mode rejection ratio, and then we get AD is going to be GM times RD over the CM is RD over 2 times RSS times dirt RD over RD. And so this becomes, so the RD will cancel, then RSS moves upwards. So you get 2 times RSS, times GM divided by dirt RD over RD. So also you can write this into 2 RSS GM times RD over dirt RD. Now, this is very important at this point because dirt RD is typically a very small number, 1%, for example, maybe less. This RD is a large number. So this is 1% means this divided this by 1%. So RD over dirt RD gives you 100. So 100 times this, it becomes a very large number. So what does it mean? What it means is that if you look at the equation over here, the ratio between differential gain and common mode gain. So the common mode gain, if the common mode gain is 0, if a common mode gain is 0, means the two transistors and the resistors are perfectly matched. So the common mode gain is infinity. If the common mode gain is infinity, what common mode rejection ratio you have? If a common mode gain is infinity, you get a common mode rejection ratio is infinity. So which means for your circuit, whatever your common mode input is, your output does not reflect any. That's what it means. What happens if this ACM is very big? Which means your CMRR is small. CMRR is small means your circuit is very sensitive to common mode input. So, and at this point you might have, what do you exactly mean? I mean, why do I have to worry about it? Well, the thing that when you have this small transistor, you have an input connect to each of the gate. You're connecting an input, a differential input. But the fact is that any wire, any trace on a PCB can pick up noise. Your two input terminals can pick up the same noise. You see? That's a common mode input because they're the same noise. You pick up the same input noise, same noise with the same frequency, same amplitude. They come to your input. So if your common mode reject ratio is high, then noise is canceled. At your output, you don't see anything. But if your common mode rejection ratio is small, this noise gets amplified, and you see at your output. This is important because at the output, I don't want to see a noise that's being amplified. I want the noise to be canceled. That's why we need to design our transistor to have a high common mode rejection ratio. Clear? Okay, so this CMRR needs to be big. The typical number, because this can be more than 100 to 1,000, and this is like 5 milli, and this to be 20K. Let's put it 10K, so we can get some numbers. So if this is 10K, and if this GM is 5 milli, and this RD is 100, how much do we get? So 5 times this one get 50. So 50 K and M cancel. 50 times 100. The typical number is 5,000. But if you want to further increase your common mode rejection ratio, what can you do then here? Well, simply decrease the variation. Make sure the two resistors are identical or close to identical. The smaller the delta RD, the bigger the volume. Okay. So that's one that we can see how we can get the common mode rejection for the RD. But the next one, we're going to look at what happens if we have this GM is different. So if GM 1 not equal to GM2. Now what we can do is we can assume GM1 equal to okay. No. Yeah. GM1, maybe what we do is this. We look at GM1 equal to GM2 plus delta GM. So we do it this way. Now we're going to go back to the equation that we had. Let me rewrite the equation. Remember here, equation here is sorry, where is that equation here? This equation here. We need to write V01. So V01 equal to minus VICM times RD over 2 RSS plus 1 over GM. So this V01 now is going to become minus VICM RD, because in this case, we assume RD is the same. Now you can, change both, then you will get okay, then we can have VO2, which is not going to change. So because we are doing is RD, we're doing 2 RSS plus 1 over GM. And so GM2 is equal to GM. So we're going to now use VO equal to VO2 minus VO1. And you can see now, this little problem over here is that this one is delta GM is on the bottom, and you can do a bunch of manipulations, but eventually we're going to use, because RSS is much larger than 1 over GM. So eventually what you get is this. I'm going to neglect the whole process. I'm going to give you the right to the answer is ACM by some neglect some differences. So this RD over 2 times RD over delta GM over GM. So this is the common mode gain that we had for the when you change the delta GM. So from here we can also define the CMRR equal to SCM over AD. Then we get this sequentially is 2 GM times RSS times so we get this one here. So basically here you can see the influence of delta GM is very similar to the difference of the effect of delta RD. So if the small change of GM will cause this CMRR is going to change. You can certainly write this one into 2 GM times RSS times GM over delta GM. So you see the ratio, if delta GM changes 1%, this becomes 100, and this becomes like a really large number, so which is good. So if delta GM changes too much, like if delta GM change, let's say, somebody designed a lossy transistor, that the two transistors are so much different that the GM is 1/2 of each other. So one is like 5, the other one is 2.5. What happens is that you get here will become 2. And this number, if we use the previous example, this becomes like 2,500, really. So not even 2,500. It's very small. Let's calculate it. So if GM is 5 and delta GM is 2.5, so 2 times 5 times 20K times 2. That gives you 2 times 5, so 5 times 20 gives you 100. 100 times 2 times 2, so it's only 400. So the ratio is only 400 if third GM is 0.5. But if third GM is 0.01, you get again the common mode rejection ratio at 5,000. Okay, so so this one is really just to look at the common mode rejection ratio. So we're going to skip the BJT case because apparently the BJT case is much more complex, but the problem is R pi that's involved. So we're going to really go over, not going to come to there. But let me talk a little bit about DC offset. Again, in DC offset, we're going to cover only section 9.4, 9.1 about the MOSFETs. We're going to not talk too much about the BJTs. So the idea that we have the same circuit, I'm going to draw the circuit again here. So we're going to get a circuit here. So this is the differential pair of a MOSFET. And then we're going to draw the small signal circuit by looking at what we have with this. If this things change, what we get at okay. So we have two cases that we're going to look at. So one case is that we're going to ground. So we're going to ground both of the gate. And in the next case, we're going to have a common mode input. So instead, we're going to connect voltage source over here. So what we're going to do is we're going to look at what happens if the two resistors are not going to be exactly the same. So what we're going to have is we're going to have RD1 equal to RD plus 1/2 third RD over 2, and RD2 equal to RD minus third RD. This is the same as what we did for the common mode rejection ratio, what we did it. But what we're doing here is if we we're gonna look at ID1. Now this is I, so each of this is gonna be 1/2 I, okay? So each of this is gonna be 1/2 I. So we're gonna have ID1 equal to 1/2 I minus GM times VOS over 2. So this is VOS. So what we are doing here is we're going to apply like a DC voltage between this one and this one. So this is not a common mode input anymore, but this is also not a differential input. A differential input always means a small signal, AC. So it will be equally divided between the input output. But what we're doing here is we're adding this DC input, which is the difference between Q1 and Q2. We add this one.
So when you add this one, you apparently can get that the VOS, yeah. So we get ID2 equal to 1/2 I plus GM times VOS over 2. So when we get this, we have this ID1, ID2, which are going to be different because the VOS, like half on this side, half on this side. But they're both DC voltages. That's why we call DC offset. And the purpose is going to bring, okay, I forgot to explain why we do this. The problem is that when you have two perfect match resistance, the current are supposed to be the same. But what happens if the RD is different? We already showed from the pre-example, the output are not going to be the same. So the idea is that if they're not the same, we want to apply a voltage at the gate such that we're going to bring the two gates at the same voltage. That's the idea. So in this case, we're going to look at what we have at the voltage of VO1 and VO2. So we can have, okay, let me write down from here. So VO1 equal to RD minus RD, well, let's do this way. Not erasing, interesting. Okay, so I will do just this. It's going to be VDD minus, this is plus, VDD minus RD times, let's call it ID1 and ID1, right? And VO2 equal to VDD minus RD2 times ID2. Now we can plug in all these numbers to here to get the actual number. But what we're going to do is we're going to directly look at VO equal to VO2 minus VO1, which in this case, the VDD is going to cancel. So we have ID1, RD1 minus ID2, RD2. And we're going to use ID1 is 1/2 I minus GM times VOS over 2 times RD1 becomes RD plus delta RD over 2, and then minus 1/2 I minus GM times VOS over 2. That's plus. So the other one is plus, and then times this RD minus delta RD over 2. Okay, so you got this equation here. So the difference between VO2 and VO1 is VO, which is this one, which is this minus this. VDD cancel, so we got this positive minus this one negative. And we plug in RD1, RD1, RD2, RD2, we got this equation over here. Now this equation is a voltage between the two drain. So what do we want, as I mentioned earlier? The purpose of adding VOS is to make this two drain voltage exactly the same. So the idea is to get this one to 0. We'll set that to 0. So by setting this to 0, what we're solving is we want to find what VOS is. So that's what we're doing. So I'm gonna okay, I can write here too. Okay, so what we're gonna do is we're gonna eliminate or connect, like the process of getting this simplified, but eventually we got VO S equal to 1/2 I divided by GM times delta RD over RD. This is VOS what we get. So the idea is that if you have a resistance difference at each sides, we will need to apply a small DC offset voltage at the two gates, between the two gates, so that we can get the output exactly the same. So examples, again, let's look at example. If, oops, what we are doing? This is strange. I have problem. So if I equal to 1 milliamp and GM equal to 5 milliamp per volt, and the third RD equal to, let's do this, RD equal to 1%, which is 0.01. And we can see this VOS will be 1/5. Again, they're both milli, so the milli will cancel 0.01. She got 0. So this becomes 0.01 divided by 5 becomes 0.002. This is only 2 millivolts. Very small voltage. So I think this will give you an idea. So when you buy a MOSFET or amplifier, and you do your design, and you find, well, no, the input and output at DC it's not the same. Why? Because the two RDs that you bought has a difference. You're not lucky because you buy them, there's a 1% difference. So now you say, what am I going to do? Well, in your design, you simply offset a little bit of voltage, 1 millivolt, actually 2 millivolts in this case, and your output will balance it become exactly 0. So that's that simple. So what it also tells you that when you buy components hardware, there's no way you can guarantee them to match. It just happened, hardware. But in your control, in your design, you can adjust. You can adjust the current and voltage. Those things can be adjusted. When you adjust them, you can get your output to be exactly matched. So this is why we are talking about DC offset. Yes. I'm sorry, can you say?
Search for specific glyphs and names.
Yeah.
And actually find those specific ones.
Yeah.
That's the way you were suggesting.
But see, when you search for the length and width, yes, you can. But you get the transistor, you get two transistors, they're not going to come the same. Even if it's from the same batch. The more matching that you have, the more money you have to pay. So, but with a you pay less money, but I still want the same performance. What do I do? Right. So this is exactly, you can adjust your circuit by control. Yes. The current. Oh, you're right. Yeah. Well, because the current is I is on one side, so each side is 1/2 I. Yeah. The total is I, but each side is 1/2. Okay. So, oh, one more reminder. On Wednesday, if I forget, when you do the quiz, remember to write the units. Milliampere per volt for GM, for example, resistance, kilo ohm or ohm, whatever. Current milliamps, voltage, volts. If you don't write the units, you're going to lose points, okay? Yeah. You do both. You do both. Okay? But once this quiz only covered the previous one. So the new homework will be the next one. The new homework is for the quiz next week. No, I think we're going to get quiz for this one because we spent so much time here. We need to have a quiz. Okay, have a good night.